how many of you have a good idea what SDN is? Okay. So for everyone else, I'll go through the introductory part. And then I'll talk about two security-related issues, because after all, this is a security conference. One, how vulnerable is this architecture? And the second part, where can we use it in security solutions? And if anyone has any questions afterwards, because I will really have to stay pretty high level, I will be around here, so just pick me up or this evening at the dinner, and we can go into as many details as you wish. I have the unfortunate privilege of being a networking engineer since 1985 or so. So I've seen so many things being proposed and failing that I cannot help myself. Whenever I see something new proposed, I immediately compare this new thing to some old thing. And it turns out that it's almost always identical to the old thing, just remarket it. And so it's immediately obvious what will go wrong. And of course, people don't want to listen until it does go wrong. And it's the same with SDN. You'll see that it's nothing new. It's primarily hype. Other things I'm usually doing are very large cloud networking solutions, as well as some IPv6 and MPLS still. So I'll start with what is software-defined networking. And the answer depends on whom you ask. So there is this one entity called Open Networking Foundation, and their definition of SDN is the physical separation of the control plane, so the brains of the network, and the forwarding plane that does the packet forwarding. So it's like you have your switch, you have your router, you have your firewall, you take the brains out, they have to be physically separate somewhere else. And now this remote brain is controlling not one device, but multiple devices. That's their definition of SDN. The acronym is somewhat weird because, as far as I remember, there was software running on the networks, starting with IBM's front-end processors. And then even modems had software. So when someone is telling me that this is now software-defined networking, I just go like, go away, you know nothing about history. But the acronym is there and it will stick, unfortunately. Now, when this thing became popular, which was in summer of 2011, all of a sudden we could see all sorts of SDN washing. So every vendor that had something which was a bit more than CLI, it could just be an API like netconf, they started calling that SDN. So for most vendors out there, when they say we have SDN something, it means we have whatever we have just relabeled it SDN because it's popular. 3 years back it was cloud, now it's SDN. And for startups, this was just a huge opportunity to hype whatever it is that they were making to the venture capitalists. So startups were selling you SDN something, and sometimes it had nothing to do with this first, well, mostly it had nothing to do with this first definition. So for example, there was a company that tweaked the TCP stack so that their load balancer worked faster. Because they had an API, well, RESTful API to be precise, which you could, for example, call from a Java applet or from a Perl script or from wherever. They called that thingy SDN. It was just a load balancer. So, SDN world is full of hype. And it's up to us, unfortunately, the users, to figure out what's hype and what's real. And mostly it's hype. So, on the other hand, I think that this is too constraining. I do think that we need to do a lot of things in the networking. We are doing a lot of things wrong. But this is not the solution for this audience. So Who proposed this definition? Well, ONF started as a bunch of very large cloud providers. And this is what they wanted. Google was building their own switches for years and years. They even have their own routing protocol because it's somewhat hard to run OSPF in one area on 5,000 switches. So they built their own routing protocol, and some small company was building the switches for them. And they were running their software on those switches. Now, if you do that, the only problem you have is that you're tied to that particular company's design. So they wanted to have a more open architecture where they could just buy switches from any supplier as long as they conform to a single standard, and of course, use that as a leverage to bring the prices even further down. That was the only thing they had in mind. They wanted to become a switch and router manufacturer, and they did it. Will it benefit us? No, of course not. Will you invest in building your own router software? No, I hope not. Yahoo had a totally different take. They have interesting problems with their network. I don't want to comment on that. But you can go and look at the presentation that Igor Gashinsky had at OpenFlow Symposium in 2011. And if I remember correctly, one of his slides was 30% of my CPU is used by the spanning tree protocol. So what he wanted was the ability to have special features. He said, I know how my data center is wired. Hopefully, I know. Otherwise, we have a bigger problem. So I don't need spanning tree. I don't need routing protocols. I don't need a number of other things. I would like to have something that serves me. And he said, and I totally understand that I will not get it from any vendor because it's too expensive. No vendor will give me my special feature for the amount of gear that I'm buying, because then they have to support this special feature in all the upcoming software releases for the next 10 years and do regression testing on it. So he was very realistic, saying, I will not get it. So I want to be able to build my own things and supplement what the switches are doing. He was not interested in low-cost white label switches. He was interested in getting his features so that his network would work the way he thinks his network should work, which is honestly a fair idea. Facebook, on the other hand, they are pretty focused on doing things that don't matter to them, like data center stuff and networking stuff and MySQL stuff and PHP compiler and who knows what else. This is not their core business. Their core business are the likes. So they are pretty open about these things, and they have even published reference architecture. Have I lost mic? Yeah. Better? No. It's on. Maybe we're out of batteries. Yeah, we're out of batteries.
I can take care of
Okay. You can hear me, right? Okay, so I yell. So they are pretty good at open sourcing things, and right now they are at a phase where they have a reference architecture for a top-of-rack switch. What they're missing is the software. And they hope that someone will miraculously appear, and somehow the open source router software will instantiate itself, and we'll solve that problem. Now, in real life, what people like us want to have is we want to have faster software development. We want to deploy things faster. We don't want to wait for, I don't know, whoever. We want to have faster provisioning. I mean, a friend of mine did an analysis of how long it takes in his organization, it's a pretty decently sized data center, to implement a new firewall rule. it's between a week and 10 days, which is ridiculous. It is standard, but it is ridiculous. So we want to have faster provisioning, and we can't have faster provisioning if we are acting like CLI monkeys and type things in. I mean, CLI is fine. I love CLI. I always say, well, we need CLI, but this is not the way to programmatically access devices. So we need programmable elements. And finally, distributed systems are great. Routers are great. I mean, after all, internet works. Somewhat, yeah. But sometimes it's great if you have central visibility into things. Sometimes it's great if you can take a look at the end-to-end path and say, OK, this is the exact path that my packets are taking. Or, an even simpler example, you know the MAC address of that phone that's not working. Now try to figure out where that phone is connected to. So you have to go from device to device to device to device to device and do show MAC address table or something to see whether it's on that particular device. How stupid is that?
Sorry for that. It should work.
Thank you.
Sorry for the interruption.
No, that's fine. Thank you. Oops. OK.
This sounds like it works.
Yeah, it works. So this thing is not bad. The idea is great. I just don't want to have the central brain somewhere, because if the communication between the central brain and my box breaks down, I have a brainless box. So this second set of requirements makes more sense for most of my customers. Okay? And on the other hand, if we talk about programmability and orchestration and things like that, we had that in 1992. We had a customer database, which was honestly a text file. We had a Perl script hacked together in an afternoon. And that Perl script was reading this text file and producing configurations for all the routers we had. And these configurations were automatically installed on those routers. So every time we added a new user, either it would be time-based or someone would click the button, and bam, we have reconfigured our network. And we were not the only ones doing that. A lot of people were doing that in those days. And well, by all definition, this could be called SDN, but we didn't know we had SDN, so we didn't call it SDN. So why did we stop? The first thing is that the networks became mission critical, and we didn't. So we had no programming skills. We were hackers. We were hacking things together in an afternoon. And if they worked, great. And if they didn't, well, we lost the network. I'm the guy who disconnected Slovenia from internet for half an hour. And I think the CTO of TailF once admitted, if I remember correctly, that he's the guy who disconnected Sweden for half an hour. So we all have stories like that. But we could afford that in those days, because no one was really making money on the internet. That was before e-banking or Amazon. Second, we didn't have any programmatic interfaces. When trying to automatically configure your devices through Telnet, it sounds scary and it's stupid, because you have no error handling. Well, you might have error handling, but then you get into spaghetti code of expect scripts. You don't want that. And then the software release changes and your spaghetti code stops working. I don't want to be there. Of course, the fact that every vendor has a different configuration syntax doesn't help. And everyone is complaining about this. And when anyone is complaining about this, I just tell them to look at SQL standard, which is standard, right? The only thing that's standardized across different database vendors is a select statement without joins. And even there is stop something in MySQL and limit something in SQL Server, or the other way around. So don't tell me we are lacking standard configuration syntax. It's nowhere in IT do we have that. It's only that other people realize that they need an abstraction layer. So if you look at any decently written software, there's an abstraction layer that isolates the stupidities of individual database vendors from the rest of the application. And we were solving that with spaghetti code, because we never learned proper programming skills. Because after all, we are networking engineers, right? So no one trusted us. So we stopped doing that, honestly. OK, so how far did we get? We want to have some centralized controllers, maybe not control plane, but at least some central intelligence. End-to-end visibility would be great. Automatic programming or configuration of network devices would be great. Now, the questions I usually get are, how is this different from the single pane of glass that was promised by the network management vendors for the last 20 years? Honestly, I can't answer this question. What happens when the network partitions? Well, we all know what happens if the controller is assisting the individual network devices. Then that assistance is gone and they will fall back to business as usual. Which, for example, you know, when Amazon lost the availability zone where their orchestration system was, the VMs kept running, but you couldn't spin up a new VM. That's the same thing here. If the network devices are still autonomous, the network will continue to work. It will even adapt to topology changes. If the network devices are totally dumb, like the true SDN proponents want us to work, then we are back to SDH and frame relay. All the backup paths have to be pre-configured in advance, because if we lose the controller, the devices are so brain dead they can't do a single thing on their own. So welcome back to the 90s. And the last one, why should it work this time? Honestly, I don't know. And then everyone is telling you how you can do SDN if you buy the next version of their gear, obviously the higher model, with a new software. And that's blatantly not true. Now, you know that in every network device you have like 3 planes. You have the management plane where you configure the device and monitor the device. You have the control plane where the device talks to other devices and collects the topology and forwarding information. Then you have the forwarding plane where the actual packet forwarding happens. You can already use netconf to configure and monitor your device in a more controlled way than SSH or telnet session. You still have the problem of having different configuration syntax for different vendors, but at least there is a standard protocol that will report an error message in a standard way, which is a major improvement over telnet. BGP is used by many people for a decade to influence the forwarding decision in the boxes. Every service provider should know about remote triggered black holing, which is the trick how you use BGP to tell everyone that this source IP address or this destination IP address should be discarded because we are under denial of service attack. Every major service provider has that feature. It's even documented in RFC. And it's been around for a decade at least. So we had SDN for a decade. We just didn't know it. PCEP is an upcoming standard that allows you to download traffic engineering tunnel information into the control plane. And finally, Juniper documented, well, yet again, it's an RFC. Juniper documented extensions to BGP that allow you to effectively do policy-based routing through BGP. It's called BGP flow spec. Through BGP, which means from a central controller far away, you could install very specific entries into every device in your network, like send web traffic that way and send backup traffic that way. And Cloudflare is using that in production for denial of service scrubbing. So whenever they figure out that someone is attacking one of their customers, they figure out what the matching end tuple is for that attack, and they install a drop entry into the edge routers of their CDN network, so that the attack stops at the edge of the network. It doesn't even come to the servers. So we can do all this today. Some people are doing it, most of us aren't. And then you have all the vendor APIs and all the scripting. So for example, on Arista, I like Arista because they are very open about the fact that they have Linux on their switches, and they give you all the tools. So you can run Perl script on an Arista switch, or a Python script, or a Chef, or a Puppet agent, whatever you wish. It's a Linux box. It's great. But still, there are some things that we can't do. For example, it would be very hard to intercept OSPF hello messages and write a different version of OSPF. And this is where OpenFlow comes in. And I will only mention OpenFlow because this is the most popular one of all the upcoming protocols and standards and so on. And on the more proprietary end, Cisco has 1PK, which is their effort to expose their API to external scripts or whatever. And they have something like 300 different APIs or so. So they plan to expose everything that is inside their software to the outside world, so that you could tweak their software in very tiny little details. Of course, there's a good reason for that. Once you start doing that, and once your scripts depend on that, there's no going back. This is the ultimate lock-in. So it's a great strategy for them. I really admire them. Now, what is OpenFlow? It's very simple. OpenFlow is a tool that you can use to achieve that total separation of control and data plane. So you have a central controller or a cluster of controllers, one would hope, and then the devices somehow connect to the controller. And what no one is telling you is that usually we use out-of-band control plane network, because it's just too risky to connect from here to the controller through these two switches, which are also controlled by the controller. If the controller goes mad, it will cut itself off from the network. So everyone sensible uses an out-of-band control plane network. SDH, anyone? We were using the same things in SDH, ATM, frame relay, optical networks, and so on. We also know what the problem is with this approach. There is no shared fate. So if the forwarding links fail, the control plane links will not know that the forwarding links have failed unless you have some mechanism that actively measures what's going on with the forwarding links. Anyway, so the controller builds a model of the topology, and then let's say you have B1 here, and then you say, I want to have prefix B or subnet B here. You don't configure this on the device, you configure it in the controller, because the devices are now totally stupid. You configure it in the controller, you say B is here, and then the controller figures out the topology of the network, figures out what needs to be done, what needs to be installed into individual switches so that anyone could reach B, and pushes down the flow entries. And now we have an entry pointing to B in every single switch in the network. So here you have 1, here you have 2 for equal cost multipath. You could have a backup entry here pointing back here, and so on. So it's traditional IP routing almost, only all the decisions are made by the central box. Okay? Now, as I said before a few times, this idea is nothing new. Functionally, this is identical to frame relay or ATM PVCs or SDH. And there are two protocols like MPLS-TP and Forces that solve the same problem. No one uses Forces, I don't know why. And some people supposedly even support MPLS-TP. The problems we're facing are always the same. If we don't have proper abstractions in the forwarding plane, it will not scale. So people who are telling you how they will reroute individual TCP sessions across your network are plain stupid. Because you can't put that many entries in the switching hardware of your switches, period. So when someone tells you how they will reroute individual sessions across your data center, no, that will not work. Then if you have central control plane, you still need some distributed resilience or you need backup paths, as we've learned the hard way. Then you have some fast feedback loops. For example, this is my favorite one. How will you do 50 millisecond convergence if the controller has to do everything? There's no way. So there are all sorts of things that we have been solving in the past, and the controller vendors will have to solve them again to make their controller work, unless they totally separate themselves from the details of the network, like every controller vendor is doing that works on overlay virtual networks, like VMware NSX or Open Daylight in some cases, or a number of other startups. What they do is they say, we will transport something across IP tunnels. We don't want to touch the network. IP is working. Let's leave it there, and we'll solve our problems across the tunnels. Surprisingly, almost every vendor is shipping something. Well, if you want to sell gear to academics in US today, every single RFP is asking for OpenFlow. So you have to have OpenFlow as a tick in the box to sell to the academics. That's why you see so many vendors supporting this, and people are playing with this. You have a number of commercial controllers, you have a large number of open source controllers, so whatever your favorite language, there is a controller for you. There's even one in JavaScript. Now, since this is a security conference, what are the security aspects of this thing? Well, I have good and bad news for you. The bad news is no one is thinking about that yet.
That's good news.
That's good news for you. That's not good news for the rest of the audience. Yeah.
There are some papers on this. Some people are thinking about this.
OK. Thanks for the correction. So I should say no vendor is thinking about this. The good news is that this is no different from all the other controller architectures that we've seen in the past. So this is not the first time that we have this architecture. We know what the attacks are. We know what the potential vectors are. We know where we can get hit. So obviously, I should attack the control plane. Obviously, I should do denial of service attacks. Hopefully, I get into the control plane and then I can do denial of service attacks on the controller, or I can do denial of service attack on the switch and hope that it will punt the packet to the controller. It's like the control plane protection in every switch or router. So, obviously, this is the first thing that we can attack. If we can get here, we own the network. Unfortunately, this is SSL encrypted.
This doesn't say much.
OK, good. So I will stop right there. I already see some people having fun.
Only optional in the OpenFlow switch specification.
Yeah, but everyone that's semi-serious is using encryption.
With self-signed certificates, I
Yes, of course, with self-signed certificates. Yes, of course. Well, there are these minor details. Let's forget them. At least we know how this is done, and we know what the usual implementation failures are, so you guys know immediately what to test. And then, of course, the controller is running on a platform, and this platform is usually Linux, so feel free. You know what to do. And then, of course, the controller itself is written in Java or some other language like that, so you know what to do. And then, because this is OpenFlow, you might have... So the way OpenFlow works is if you receive a packet on a switch and you don't know what to do with the packet, you might decide to send the packet. Well, the controller might decide to program the switch to send the packet to the controller. This is how ARP is done in most cases. Which is great. You just start an ARP storm and you flood the controller. Game over. Well, no. The switch will flip over first. The CPU in the switch, we're always joking, is the thing that costs 10 cents. So the switches simply cannot flood the controller because the CPU is not powerful enough to send so many packets to the controller. So smart vendors have realized that, and what they have is they have control plane protection in here. So they're limiting the amount of packets sent to the controller. Which, of course, brings you back to the other usual attack. If I can't kill the controller, I can always kill the control plane protection on this switch and prevent anyone else connected on this switch from working. But this is no different from traditional switches. You can do the same thing on traditional switch. Once we had, I think it was CRS-1 from Cisco. And we just started flooding it with ARP. On a single interface, we generated 30% CPU load. That's how things work. I mean, let's be realistic. And so, of course, once you install control plane protection, that goes away. But it also means that if someone is flooding this switch, no one else will get their ARPs in. That's how switches work. And then, of course, we could do some other thing. We could do packet spraying, and if the controller is stupid enough, packet spraying will result in numerous requests to install additional flows, and then the switch will flip over, because the switch can only install a few thousand flows. Or even if that doesn't happen, because the switch is smart enough to age the flows, the controller will continue to send new flows because the packets will continue to arrive to the controller. So it's effectively the same attack that we had in the good old days when Cisco still had fast switching. You exhaust the cache, bam, game over. So, of course, the first thing you do is you have separate data in control plane. That's the most obvious thing that you do. And then you hope, and these guys will prove you wrong, then you hope that the switch separates the management traffic from the forwarded traffic in a proper way, so that there is no connection between the two. Yeah, he's smiling for a good reason, but at least that gives you a fighting chance. But it's like any network where you have some control plane. Once you get into the control plane, it's more or less game over. And if there is a way to get from the data plane into the control plane, it's game over. The other thing that you should look at when you talk with the controller vendors is, how do you set up flows? Do you set up flows based on known topology, which could be whatever you get from the orchestration system in OpenStack environment, or whatever you get from vCenter in VMware NSX environment? Or do you actually set up flows on demand, which is reactive flow setup? Because if you set up flows in advance based on known topology, then no one can exhaust the controller. No one can attack it through the data to control plane interaction. If, on the other hand, you have to do dynamic MAC learning, or if you're doing firewalling or load balancing with the controller, good luck with that, then of course things have to go to the controller, and there is always the chance or the option of doing a nice denial of service attack by just spraying the packets all over the place. And of course, you have to have some sort of control plane protection here, so that if the application, the controller, is using reactive flow setup, at least the switch itself will not allow the controller to be flooded. You know how well control plane protection works in traditional switches. It's usually just a single token bucket between the data plane and the control plane. It's never tied to an individual interface, at least not in most cases, which means that one tenant on one interface can host the whole switch. But as I said before, that's nothing new. We had that before. So, use out-of-band control plane, minimize the control plane involvement, use controllers that are not setting up individual microflows, because that will not scale, and go with something that has distributed intelligence. Because if you have centralized intelligence and someone gets into that controller, it's game over. Okay? And then you have the traditional switch hardening guidelines, like strict control data plane separation, make sure that the switch cannot leak packets from one into the other, and control plane policing. And finally, the controllers run on whatever operating system, and you know how to harden the operating system. Or if you don't, you will have to learn it pretty fast, because the vendors won't do it for you. Now, let's be more positive. Boring? No. Can we use this in some real-life use cases? And yes, people are using both SDN and OpenFlow in a lot of different applications, and I've just picked up 2 or 3 security-related ones. You know how well network monitoring works, right? You have interface counters, which are totally useful. You have net flow records, which are too granular. And you have S-flow records, which are statistical. Well, you have S-flow export, to be precise. And on the other hand, you only see MAC and IP and ARP tables on the directly connected switches. You can't see this MAC address over here on this switch. So it's hard to find information about the network. It's hard to measure whatever you want to measure. Now, luckily, and this is one of the good things in the controller-based networks, the controller should know everything about the network. After all, that's the definition. So you should be able to figure out where individual IP addresses, MAC addresses, ARP entries, and so on are. And there are controllers on the market that can actually show you that. So if you have a data center fabric with a few tens of switches, you can actually see in the controller where individual MAC addresses are, on which switch, on which port of which switch, because the controller has this information anyway. So of course, you should ask yourself, how is that different from a decent network management system? And I always ask back, can your network management system do that? Usually the answer is, next question, please. So of course, there are software solutions out there that do that already. But I hear so many networking engineers complaining about this that probably there aren't that many good solutions out there. But it's just a software problem. Second, if you have the right hardware, and now we are coming back to the hardware, OpenFlow is a great standard, and OpenFlow allows you, in theory, to do an enormous amount of things. Like you can replace an MPLS tag with a VLAN tag. And you can do destination port rewrite while doing that. So you can do anything you wish on any header field in the whole 4 layers of headers. Unfortunately, not in hardware. The hardware can do what the switch hardware can do. Just because you install new software on the switch, you won't get new hardware functionality from the switch. So the switch hardware can do what the switch hardware can do. And some hardware can count packets associated with a TCAM entry. So it's basically its access list per line counters. Only now you can access them through OpenFlow. So what you can do is you can install flow entries which all point to the same next hop, or they just point to normal processing, but the counters on those entries increase, and so you can measure the traffic that matches this flow entry. Okay? So it's not like NetFlow, which is every microflow, or SFlow, which is statistics. You can actually say, I want to measure this, and then you get the counters. If your hardware supports that. Otherwise, you will get zeros instead of the counters, obviously. And people are using that in IDS solutions, and I'll show you how. Before going there, there's one other. How many of you are doing, have built tap aggregation networks in your data centers? So you have taps, you have span ports. Now you need to collect all that and bring that to the central monitoring or whatever tools. And there is a company out there that does switches that are specifically designed for the tap aggregation networks. It's called Gigamon. Has that bright orange color, so you can always spot them in the data center. And they have an excellent product, which is also reassuringly expensive. Turns out that that product does the same thing that any top-of-rack switch with merchant silicon could do. And this is where some top-of-rack switch vendors have seen their opportunity. Why would you buy something that is 3 times more expensive than my top-of-rack switch, which does the same thing? And now the problem always was, how do you configure this thing? And it was access control lists and policy-based routing and who knows what else, and we are all so sick and tired of that. And now you can use OpenFlow. And the beauty of OpenFlow is that you can actually use the same OpenFlow application to program switches from multiple vendors. So you solve the problem once, and then if you don't like the switch vendor, you can just replace him with someone else who has approximately the same functionality. And just today, someone sent me a link to a presentation at the Wireshark SharkFest, where Microsoft is explaining how they are doing exactly this in their data center, using OpenFlow to program the tap aggregation switches to get the traffic that they want to see at a particular monitoring tool. And if I understood that presentation correctly, they even go as far as using SFlow to identify anomalies, and then the SFlow collector would trigger the OpenFlow controller to install the forwarding entries so that they start collecting the information about the anomaly. How cool is that? Or, instead of using span ports, imagine that you could say, instead of span ports, let's collect port 80 on this input port and backup traffic on that input port and port 443 on that input port, but only if it goes to a specific server. So instead of mirroring a whole input port to an output port that we're doing today with the span ports, you could install fine entries, granular entries, saying, I only want to see this particular traffic. Please mirror this thing. And you can do that with OpenFlow, and people are doing that. And the other thing that people are doing is scaling the IDS appliances. So, you know, if you have a 10 gig feed, I don't have to tell you that, and you have 1 gig appliances, you have a problem. So, of course, that problem is easily solved. You use a regular switch and you configure default routes pointing to all 3 appliances, and the traffic will somehow miraculously be load balanced across all appliances. The only problem is that we usually use 5-tuple load balancing, which means that the traffic from the same source IP address could end up at different appliances. So you don't have a whole picture of what a single source IP address is doing. And here, because you control the traffic distribution through, for example, OpenFlow, you could say all the traffic from this address range goes to this appliance, all the traffic from that address range goes to that appliance. And if one link becomes over-congested because someone is really doing something stupid, you figure out what traffic is coming through that, and then you split that in half, for example. And there are people actually doing this. For example, I know that the University of Indiana has this in production. And the beauty of this is you are actually doing this after the span port. So this switch doesn't have to be in the forwarding path. You just use the span port on the forwarding path to get all the traffic, and then you insert this switch to distribute the traffic. So this is totally off the forwarding path. It's not in production, sort of. So you can play with this. And going one step further, once these appliances detect that something is wrong, they can isolate the flow information and tell the OpenFlow controller to drop that flow. And Bro IDS actually has the module for that. For those of you who don't know Bro IDS, let me do a plug. There is a presentation in like 2 hours in the other track where one of the Bro developers is talking about what their tool is doing. Honestly, I don't use these tools because I know nothing about security. But some security people are very excited about Bro, so go there and listen to that talk. Now, the real question for all of you, should you care? Maybe. Now, concepts are interesting. Regardless of what I think about the whole thing, and I think a lot of that is hype, the concepts are valid and interesting. And the concepts will change the way we do networking. I mean, people disagree on that, but they will. Maybe they will not change the routing protocols, they will not change the forwarding paradigms, but hopefully they will change the way we deal with networks, because the way we deal with them now is stupid. Centralized computation and some interaction with the management plane, for me, makes more sense than centralized control plane. Particularly in WAN networks. You don't want to have central control plane in WAN networks. We've been there, we've seen how well that ends. OpenFlow was a big hype a few years ago, and right now it's becoming quiet. Because people have realized that it's just a low-level tool. It's just this one small Swiss Army knife that can do anything. But sometimes you just need a bigger hammer, not a Swiss Army knife. And the initial use cases, large data centers, large cloud operators are already using all these concepts because otherwise they cannot survive. And some of this is now trickling down to smaller data centers, and eventually we'll see these concepts in the enterprise networks. The whole thing is still very immature. It's only 3 years old. Standards are changing, ideas are changing, solutions are changing. So this is not something that you can buy tomorrow off a price list of your favorite vendor. Well, maybe they will try to sell it to you, but it's a different story. And go and install in your production network, and it would just miraculously work. We are not there yet. But it's definitely something worth considering. You have to figure out whether it fits into your network and you have to say, okay, it fits and I will pursue this further and see where it leads, or it doesn't fit and I'll revisit this decision in 3 years. But ignoring it wouldn't be a good idea. And this is no longer an academic exercise. There are commercial products out there, and for example, NEC has their programmable flow, which is a data center fabric solution, and it's been shipping for 3 years almost. So there are commercial products out there that aren't revision 0.1 anymore. Now, if you want to know more, because it's obviously impossible to squeeze everything in 1 hour, on my website there are a number of SDN webinars, and the ones that are circled in red are publicly available. So you can just go and watch them or download them. They're all downloadable MP4 videos. And the best way to get there, ipspace.net/SDN. Can't get easier than that. And if you have any questions afterwards, please feel free to send me an email. I always reply to emails. Sometimes it takes time, but I always reply. Or if you like Twitter, just send a tweet mentioning me, and I get like 3 mentions a day, so I can still reply to those. And some of you might be looking for a certain 16-digit code, and it's somewhere on my web, and no, this is not a hint. Yes, it is. And there are also a few offers for the Troopers attendees there, so go visit that, see whether you'll find the code. It's pretty obvious. So, thank you. I hope you will test SDN in your networks in some future.